Okay, how many CLAs we have in the room? CLDs? It's about half of the room, total, maybe a little bit more. Well, the same as we had like last year. Who came to my presentation last NIWeek? Who? We got a new crowd, only about 10 people. So I'll have to repeat something. Okay. My name is Dmitry Sagatelyan. I'm a CLA, LabVIEW champion, and I'm a regular presenter at the CLA Summits and LabVIEW user group in the Bay Area. I come from a computer science and software engineering background, and as such, I'm passionate about bringing modern software engineering methods and practices to the LabVIEW community. My main areas of interest include vector programming and using agile design principles to design better LabVIEW architecture and code. I started Upper Technologies in San Francisco Bay Area in 2009, and I'm actively using solid design principles for the last 7 years. Got really good results with this, and as a consultant, I can spare you some bruises and pain and help you learn solid design faster. So I hope you learn something from this presentation. This is a typical situation where you find yourself. You have internal reuse libraries, and you have an application that calls methods, classes or APIs from those reuse libraries. And those libraries generate errors. The solid circles are setter or generate error calls. The hollow circles are get error or error handling calls. And internal reuse libraries handle some of the errors, but the rest is passed to the following application. And it so happens with error handling and with logging that such calls are permeating the entire application code. Now your application is successful, marketing has come in, and tells you to add some features, and you're lucky to find a third-party vendor library that covers part of it. That is good, it saves you time as code reuse. And that reuse library also generates errors, handles some of them, and you have to handle the rest. Use the red column circle. And then it goes, you add more and more libraries, and your entire application is in error handling. If you do it right? You don't skip on error handling. And there are two problems, two challenges that I see with this. First, how you design error handling to keep your application lean and scalable. What, for example, happens if you swap one library for another, and the error handling style changes? How do you handle it? Do you need to refactor your entire application for the no? And the second, some libraries return more information than there is in an error cluster. They added by different means. So how do you handle different error cluster payloads in your application? So these are the two challenges I have to answer myself. Another thing, in the last 5 years, all my presentations show slides with this book. Other people like Alan Smith and John LabVIEW also have this in this book, Agile Software Development. It describes the solid principles, the five solid principles here, plus extra 6 principles for package management. And I would focus on using the solid principles here. John LabVIEW and Alan Smith did a really good presentation yesterday on the Wednesday about the packaging methods. You may want to look at that slide. So there are really 3 reasons to use solid principles. If you consider them important, you should buy this book and start reading it. And the reasons are, if you practice solid principles, your code ends up lean and scalable, if you consistently practice it. Second, if you practice solid principles, you can refactor your code, your application code, to changes in the requirements at incremental cost. You don't need to throw away the entire thing. You may need to refactor only the subsystems that were affected by changes in the requirements. And the third, which was important for me because I write to use libraries, is when you practice solid principles, a lot of your code tends to be reusable with no or very little extra effort, which means you'll get more productive on the next project if you're doing a similar test system for a different vendor or a different customer. I won't be referring to code reuse in this presentation, multiple places, so I want to make sure we're on the same page. When I say code reuse, I mean reusing something developed in a different context as it is, without any changes. And some people like to package reusable code like in binary or password-protected packages, so you don't make accidental changes. And this is different from code recycling, which follows a familiar pattern. You take a useful code snippet VI, library, or class, you make a new copy in another project, you make changes to the copy, you debug, you test it, and then you have to maintain it. And chances are you will end up with multiple very similar copies over time, and each of them would need to be updated if you fix an error or need to add a feature that is common to all of them. This is more expensive. We do it all the time, but it's more expensive than having one copy and then recompiling and redeploying it to every system. So code reuse is as easy. That's what I will be referring to. Presentation outline. First, I'll briefly review what we have in current LabVIEW for error handling. Then I'll talk about why it is not enough if you're designing mid-scale or large-scale systems. Then I'll talk briefly about error handling best practices and go over in details on my error handling library and logging library, which work hand in hand together. And then the final one would be covering some optimizations and benchmarking of the overhead. So that's the plan. And I'll take questions as we go. I may defer them to some slide further down or to discussion if they take too long. So if you have a question, just ask. So what we got in LabVIEW. This is one of the most used features in LabVIEW, error cluster. Everybody knows this. Everybody uses this, hopefully. And many people hate it because it's not scalable. What it has, it encodes three states: error, no error, and warning. That's simple, that's a Boolean. It encodes error ranges in an I32, and there is about 60 error ranges as of LabVIEW 2015 for all NI products, and NI maintains those ranges, but there is no single list where you can find all the error codes. And there are 3 ranges that are devoted to customer codes. It's this, about 100,000 error codes, and that's pretty much it. The source field is much more complicated, and that's where your problems start. You can, for example, execute a primitive, and it will give you this value for the source file. If you use error cluster from Error.code, depending on whether you connect custom message and show call chain, it will give you 4 options. Different number of lines, and there is a tab error and tab. So parsing this text out of the source field can get complicated, and you don't want to have this parsing code in your application, obviously. And the usual way people try to add data to error cluster is adding more fields, encoded fields in the source. So if you have a third-party library, there are chances it will add some data, but you won't be able to parse it easily. Primitives. I use these ones, they're really good. Merge errors to propagate stuff, unbundle, case statements, you can substitute, connect an error wire to a Boolean input, compiler does the work for you, that's good. And historically, I don't use this because I came up with my first error handling extension in 2002, and I could avoid it. And I'll talk about this extension. There is another really nice feature, it's called LabVIEW error ring. Who uses LabVIEW error rings? Perhaps 20%. It's a very special animal. This is the error ring, and you can unbundle it. It has the same fields as the error cluster, but you cannot drag it into an error constant. You cannot convert it into an error control or put it in any other way on the front panel. Probably there is a good reason, I don't know why, and I don't care because I don't use them. They came out too late for me. And this is what an error ring. When you configure it, it has the error warning sign, whether it has a whole chain or not. This is your error code, error message, and an edit button. And the edit button, when you hit it, opens up a dialog to configure the code. And if it's a custom code, you can enter your own message. Otherwise, it would pop up the message for this code from the LabVIEW product. Do you see it, or I need to zoom? Okay, let's not zoom, that makes things more complicated. So if you put in this kind of string with the format specifiers, it does some magic. And this is timestamp and a floating number and a floating number. This error constant grows down, and it allows space to connect three of the specified values. So what you get is this error message. So it may get even more complicated parsing the string because you can't put your custom content. Wonderful feature, by the way. I like it. There is also a very useful thing. It's called error LLB, and it lives in vi.lib utility. It has some very useful things. If you didn't look at them before, look at them. My favorite is the Error.code database VI. You pass it an error code, and it returns you an error message for the error. And it does it in 80 microseconds at any point. It's really efficient. Another one, which people use often, is the error dialog, which boils down to call it detailed display dialog, which pops up this window. Okay, so I'm done with the overview. Now the issues I have with LabVIEW clusters. First, I spent a lot of time designing reusable code and maintaining it. And sometimes I use third-party toolkits and libraries in my application. And NI is in a position to manage the error ranges for their 60 products, which is good. But there is no governing body to manage the same for the customer code. So what we usually get is an error code value collision. And that's not good if you start using third-party libraries. You can manage it within your internal reuse libraries. Chances are you're using the same 5,000 to 9999 error range. So what solution I came up with? Instead of an error code, I'm using two entries. One is the error scope,
which is the name of the LabVIEW class that declares this error, not generates, declares. And it's guaranteed to be unique because you cannot download, you cannot load into memory to classes with the same name. And then it's an enum, and each class defines an enum which lists all the errors that it generates. So that's issue number one. Second issue. Most of my code these days is by-value classes, and I use actors all the time. And many applications create multiple copies of actors of the same class. So when LabVIEW returns an error, there is no indication which copy returns that error, right? You don't know. I have like a monitoring system for a motor yacht with 4 diesel engines. Which of them has something bad happen? No clue. And there are clone names which are numbers behind the class name or VI name, but they are hard to use because they may change the numbers from run to run. So you cannot rely on those. Solution? You need some way to add the name of an object, of an instance of a class to your error, which you return for error processing. That's kind of obvious. And you may add it encoding with a tag or some other way, but it's better to do it. It would make your life easier. Adding custom data. There is no clean way to add custom data to error cluster. And people, as I said, use like ad hoc ways, ad hoc tricks like error and append. I used a completely different tab in my earlier implementation. So that makes you incompatible with other stuff, with third-party code. So the solution for me was really simple. Instead of using error clusters as they are clusters, make them into error objects. And this way you can update it to your object, whichever you need, and pass it through error wires. And in this case, that's data I pass with my implementation. You can have yours using this token. And it includes object name, as we talked, the error owner, the class that declares this error, and it's an internal error of this class. Error name, I don't use iteratives, I use the unknown strings. One thing that is good about text-based languages is that they don't use error codes. They use defined constants in the .h file. So I wanted a constant in the .h file. Timestamps are usually important. Everybody needs timestamp because there is a propagation delay between when you generate an error and when you start processing it. And the call chain. And in this case, it's a parsed array of strings. And this is important for lower overhead, so you don't need to parse the standard call chain when you process the errors. And number 4, I think this is the last one, is incompatible error handling extensions. I already talked about them. So what I really need to avoid this problem with flagging my application code with parsing different formats of errors is to have a wrapper library that decouples the application code from how you decode errors. So this is the way I went. And it nicely works. This is a way actually recommended by the dependency inversion principle. Identify dependency interfaces and don't statically link into concrete implementations. Link into the dependency interface. That's a standard way. So I think I'm done with the issues. I'm not the only one who tried to solve this. There are several error handling libraries out there. Just a few, I never use them. I just pull them here so you can see those. This is a really nice library. It uses the PEP and error tests, so it's compatible with LabVIEW error cluster. MGI error handling library. I don't know what MGI reporter is. It also uses this test. OpenGR library, which I think is more like a wrapper. It doesn't do really error handling. And there is a thing by NI. I think it was designed for use in RT. You can get it for either the tool networks or an NI.com. And the rest are available on tool networks. And this is kind of a helpful reading, besides what I'm telling you here. This is an earlier presentation by Chris Rell, who is missing from this NIWeek. This was done in 2009, so 8 years passed. But you still may want to get it and read it because it has many of the ideas I cover in this presentation. And the document, the white paper for the GPower user guide is also very nice because it cleanly lays out how to do error handling in LabVIEW and what features they had, etc. So if you're curious, just look at those things. These are my attempts at error handling. I started doing it in 2002. And the first thing I did, I started using Error.code and Error.code instead of just Error.code, the way I described. And I encoded it in the payload, in the string field, and I used proprietary tags. It worked for a while. There was no classes at that time in LabVIEW 6.1. But then around 2010, I started shifting my development to classes. And in LabVIEW 2010, I did a complete redesign of error handling for my reuse libraries, which were kind of solid compliant. I just started learning solid design that year, so I didn't understand it, of course, really. So this was kind of compliant. And instead of proprietary tags and encoding for encoding payload, I started past the flattened object. That's the major step. There was a single error class that was defined that was not extensible. And there was recursion in LabVIEW 2010 as opposed to 6.1, and which made error handling easier because in error handlings you have to handle internal errors and you don't want to write a completely similar layer of code to do internals. So that made it leaner. And the final attempt I did was in 2015 when I replaced error codes with error names. And I actually now allow customers to define their own error clusters, error objects, and they will be passed through the error wire just as my limitation is. And multiple types of error object can be passed to the same wire and handled by the error handling range. And it is completely solid compliant to the current understanding of solid text. So this is my history. It was a lot of work, but I consider error handling so important that I invested a lot of time. Any questions about it? Good. So now let's go over best practices. I chose like 4 of them. The first, most important, is the pay grade principle. It says handle all errors as close to the source as possible. And return an error component only in case a VI cannot recover on itself. And the real reason you want to do it is because when you pass the error up, you lose part of your local context. Let's say this is where the error was triggered, and this is where it was handled. You retain only part of the local context. But at this point, you get enough global knowledge to properly handle an error. And in order to do this, sometimes you need to add custom data from the trigger point so that the handler can get information. This is motivation for actually introducing custom error tables. This is the main motivation. So this is the pay grade that goes up and down to up, like in our career path. Number 2 is when you cross abstraction layer boundaries in the call step, consider translating the original error into something else. It is very unhelpful to get an error resolved when you try to allocate an image and there is no memory, and it says there is no memory, blah, 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 without telling that you're trying to allocate an image and where it is happening. So this is the second. The third one, avoid temptation to return multiple errors to caller. The papers, the toolkits I mentioned, some of them make attempt to return to stacked errors. I try to avoid it because I think it's a smell of violating the single responsibility principle. And if I absolutely need to return multiple errors handled from a single VI, I will start looking how to redesign it and split it into independent parts. And the fourth one is about error handling in reuse libraries. A VI in a reuse library should not make assumptions about the caller's context, because it may be called from many different places for many different reasons. And this is why, for example, I consider returning warnings and not pattern, because what it does, the VI that triggers a warning makes an assumption about the calling context. So those are the 4 practices I usually follow. There are more, and there is a reference down in the presentation where you can look for more. Okay. Before we get to the code, one more important thing. There are 2 broad types of errors, bugs and exceptions. Bugs are flaws in our design and code, and bugs need to be detected and fixed. While exceptions are conditions, abnormal conditions that are encountered during program execution. And detecting them is not enough. We need also to handle them without terminating the program. So these are 2 very different use cases. And for example, for a fault tolerance system, all exceptions should be explicitly listed in the requirements or in the spec or whatever. And that list should mention how they need to be handled. It's a feature of the program. And of course, when you write an error handling libraries, you need to be able to handle both use cases because bugs and exceptions are intermixed. There is no way to figure out which is a bug and which is an exception, except by returning to the caller. So what this program is, what this method is, it is a constructor for my application assembler. It starts the environment in which the application would run. So what it does, first here, it initializes my reuse libraries. Then it looks and gets the environment I'm running in, and from the application name it generates the path for configuration file. In this case, a sample file. It sets the format of the NAND file, that's a class. And in this case, this is MGI read-write anything, which I love, deeply love. And then it passes that name and attempts loading the configuration. At the same time, it takes the UI, the GUI VI reference, and retrieves a string control called global sync and returns it to be used for creating, instantiating the global log. Because I usually log into different areas. It's a text file and a string control on the UI. And this global log uses configuration retrieved from the INI file. So I create the global log. At this point, I can start logging errors and I exit the initialization. So there is an exception. There is an exception here. If the configuration file does not exist, it's a runtime condition I need to handle. And the way I handle it, the way it's specified in the requirements is there is no file. I return factory default configuration, and I create a new file with the expected name with those factory default values. So this exception doesn't happen next time. And then here I log it. And that's pretty much handling an exception. So whoever started the program knows there was no config file, but the application started and I can use the log to troubleshoot what is going on. On the other hand, not being able to find a string with this name on the UI is a bug. Somebody may rename accidentally or intentionally that string control, and I cannot find it anymore. It needs to be fixed. And in order to be fixed, it needs to be detected. So I also log this bug and try to start the application. And the only fatal error is if I cannot start a global log. So I won't be able to return any valuable information. So I just go and pop up a window and say, well, sorry, cannot instantiate the application. So that's pretty much it. That's the difference. My mouse. That's a gravity thing, you know. Racing cars, it just goes down. Okay. Let's turn this guy. So let's switch to the error handling classes I wrote. These are the requirements. These are not the formal requirements for a customer that Becky was talking about. This is for myself, so I clearly understand what I mean from error handling. And the first one is prevent error code collision. We talked about it. Support passing object names. Support customer types with developer-defined payloads. Handle multiple customer types. Test both LabVIEW errors and flatten custom error objects via wires, error wires without creating ripples throughout the code. If I wire an error with a flattened error object, it should still behave correctly, right? Support customer error dialogues, return error source, error scope, error name, etc. Do not support warnings. I explained why I don't like that. And do not support aggregating and passing multiple errors. All support event reads. So these are the requirements. And this is how it ended up. You have your application code. And you have three pieces in the library. The main one is the hard error interface, which defines common functionality and handles the internal errors. And the rest is implemented by a concrete implementation. This is called host, because I use it on the host side. On RT, you may want to do something else. Because you saw the error cluster, it has a loss of strings, and you may not want to do it on RT, use it on RT, because you increase jitter by allocating memory per string, right? And then there is this wrapper that actually does the get error calls, and which becomes the dependency interface for application code, and it belongs to the application code. And in order to introduce a new error class type, you would need to extend this LBD. So you would be refactoring it. But I use it out of the box as is because I'm happy with this error class implementation. There are multiple ways to extend it. First, if you want to just add extra data to what I have, you create a child class and possibly update some of the dynamic dispatch methods, or you can change the behavior without adding more data by just a variety of the methods. If you don't like the host error, like on RG, you can implement stuff from scratch using the host error class as a template, not a template like recycling. And then there are third-party error handling extensions. They have nothing to do with my reusable code because they don't use this implementation. But you need to add code so that the hard errors wrapper can properly parse the error payloads and return the required data application. So that's pretty much it. How does it look? It's very simple. It is lean. You have this error cluster, error object that I create when the error is generated. And this is the wrapper library. It cares about cleaning errors, getting error information, getting error message, and popping out an error handling. This could be get error and get message like a single call, but they have two different use cases. One is for handling an error, another is for logging. And since I already have a lot of outputs, I decided to split those. But they have two distinct uses. Clear errors is simple. It takes an array of error names, scope, and source, and will clear only those errors. It looks through searching through the array. And this one pops up a dialog just like the LabVIEW did, but it has some nice extensions. And I can actually try to show you one with it. I think you would like it. That's the one. So what I do here, I'm creating a new error, triggering an error, and then call it just this guy. And it would open the continue dialog. Okay, let's run it. This is your continue dialog. And it lists all this data because it's implemented in my host error implementation, and everything is nice. And then there is this little button that pops out the call step. And these are all clones. Okay. Click on the clone, and it opens the clone. So now I can actually highlight execution or move that breakpoint. So this is a little thing that really helps me debug clones. And if you don't have one, you may want to create one. And if you want to do like this thing, it will display you in a board dialog. It's the same code, just it populates different one. So that's a nice feature. Let's get further. The code is really simple. What I'm doing here is, this is the get error info method. I'm taking the error cluster. I'm checking if this is my error type, my flattened message. If it is, I convert it from the flattened to a class object and call a dynamic dispatch method for the class, and it returns stuff. And if it's not my flattened object, then I return LabVIEW as the error scope and the string with the error code as the error name. Very simple. And if you add your extensions, you would be adding another frame here. You need to catch that it's a different type that you want to handle and add some code here. This is why this error or this wrapper is recycled. Simple error object, simple error dialogs does it the same way. It figures out whether you want to display this error or not, and what type is it, and if it's my flattened error. It calls a dynamic dispatch method that is specific to the error implementation class. So if you redefine the class, make a child, it will call your dynamic dispatch method, which is nice. Setting customer. errors. So the library has two public methods for like normal use: set post error, the class is called part post error, and set post error from native error cluster. The two use cases, it just creates an object, error object from this inputs. And this one takes the error in, which is a LabVIEW error, and adds scope and source information and converts and flattens it and returns it from the error. And you see there is no error object coming out of here, so the caller is never exposed to your concrete implementation of the error class. And there are these three methods: get, error, info message, and simple error dialog, which are dynamic dispatch, and which implement the abstract methods in the interface code. That's pretty much it. Nothing more. This is the code of set error. It takes all the inputs. It parses out the call chain if it needs to be there. It converts, it generates a timestamp value if it was not there, creates the object, flattens it, and passes out. And if you say log the error, it would log it to the global log. Not a lot of things to do. And this is the how I create, convert LabVIEW errors into the error objects. I parse the LabVIEW error and call this very same method. Also very simple. Now, every class that generates, has internal errors, need to generate it, and there is a dedicated, protected set error call. I have an enum that defines all the errors that may be generated by the class. And then I call an internal VI that actually maps those error names into the error text. You can add an extra postfix message, and that's pretty much it. So I have a class that needs to generate an error. Then I have to have this method in. Let's say I have a class hierarchy. This is one base class, one set of errors. Its child is an actor, defines additional errors. And this is a UI, which is an actor, defines additional errors. Each of them have this method, which will be called internally by the class. And all of them call the set post error method. And this is the only point where my reuse library code is statically linked to implementation of the error handler. So it's easy to change if you need to change it. But I don't, so I don't do it. Two last things about error handling is how you convert, how you flatten and unflatten errors. Flattening is simple. You check if the error object is valid. There is a way to check it if it was properly initialized. And then you just set the code value to whatever you chose and pass a flattened object and so in the process. Unflatten is a little bit more convoluted. What it does, it takes an error cluster, checks whether it's a flattened error, and if it's not, it returns an error to the caller over this wire. It's an error object, and it always returns error, duplicates error in the error object. So if it's not an error and I made this call, it means at this point I made a bug. I need to fix it. And this detects it. Now, the next step, if it's my flattened error, I try converting it to the error interface class. And if it does not convert, I generate another internal error. Because that's not what I'm expecting here. But if it does convert, look what happens. I just pass out the error. Like in the actor framework, when you flatten and unflatten message objects, you need to convert to your interface class. And then you will be able to call all dynamic dispatch methods on that wire. So you don't have to test for concrete implementations of a class. This is enough. this is a really powerful way to do it. Yes?
So if you have that RT error enum that kind of flags it would be one of your special error classes?
This one.
Yeah. How do you avoid or minimize conflicts with potentially some other errors in that same code?
It is a strict type def defined in my code. If you want to change it, the value is 9999 actually. So this is a custom error code. If somebody uses it and you want to put this code into your application, you need to change it. And it's easier to agree on one error code than on a range, right? So this is like, it's not perfect, but it works for you. Okay, logging, I already showed you that logging can be used as a form of error handling. And this is the way I do logs. I usually have tabs, and one of them is a log file with the string control that I showed you before. And the good thing is I can, without changing the code, at runtime, I can change the detail level of what is logged. And this is done by introducing log levels. This is a master switch. If I say debug, all log calls with values that are more important, like minor, major, imperative would be logged. If I say major, only the major and imperative would be logged. And if I say off, nothing would be logged. This is the master switch. So you can tune up at runtime how much stuff you want to have here. And over the years, it appeared to be really, really important. And you can usually do your log outputs when you debug with the debug level, and then forget about it, and your customer don't get all those nasty bug stuff which he doesn't understand and start calling. Now, this is the log subsystem requirements, and I explain why I wanted to do it this way. First, support multiple independent logs per application. One log is not enough. Support multiple syncs per log. A sync could be a string control like here, a text file, or a database. And you make one call to the global log or another log, and the same message will be called with the same time, would be logged with the same timestamp to all syncs. Support sharing log syncs instances across different logs. This way you can merge your errors. I never used it. It seems to be a cool feature and doesn't cost anything. Log detail filter, I already mentioned it. Support starting, pausing, and resuming, and stopping the log at runtime. So there are VIs to do, or methods to do that. Support single global log per application. It should be singleton, because I don't want to pass an extra wire. It clogs the diagram. And I'm guaranteed that all parts of my code would log to the same global log. And the very important thing for me is log design shall not increase caller code complexity and readability. The connector pane should be simple and it should not require extra wiring. So these are the calls to log to the global log. Not much error in, error out, a string which you want to log, and the level of severity. And logging an error of level of severity, and the error to be logged. If there is no error, it doesn't log in. So the diagram is depicted here. We have a single application that uses multiple logs, and each log can use multiple things. And the use case for this scenario is you have a test station that needs to simultaneously handle multiple DUTs independently tested. And when you create an actor for each DUT, you generate in your application a log object, you pass it to that DUT actor, and it starts logging to that log. This is dependency injection. And all bugs and all activity of the test station is logged to the global log. So it's a natural solution for test station. This is the structure of the logging library. Again, you have an application. In order to log, it needs to call one of those methods, log message, log error, log string. Message does some formatting and then calls a log string. And this is a way to add and remove things at runtime. You have a global log, which can be called, and wraps a log file. And then you have dependency interface, the sync interface, which consists only of one method, log string. And I implement different things, like a text file or a text display thing, and I need to implement only this one. That's all library. And for the requirements, the design is pretty easy. I'll skip that part. Interface details, I talked about that. Another thing you want for the reusable log is simple configuration. So I chose these options, the log level for the log, enable, disable, and call chain display or not. And for different things, you have different configurations. Because for a file, you need a folder name and a file name, whether you want to manually put a timestamp, whether you want to append it or to write it, and whether you want to flush on an initial operation or not. Because when your application is crashing, you want to flush everything. Yes, sir.
What are your log levels?
I'm sorry?
What are your log levels? How many levels do you have?
I have 5. I had more, but I discovered I don't need them. So just keeping them, simple. And for string control, it's about resizing because you don't want to log 100,000 lines to your string, which will kill your application performance. So what this does, it keeps between 100 and 200 lines in the string control. And if it starts adding more than 200, it cuts the intent to 100. So it jumps, which allows me to avoid blocking the application. This is the long string method, very straightforward. This is an object. You pass the level in the string. You determine whether to log or not. And if you do need to log, you take all things and iterate through these things. Nothing more. Now this is not optimal because things are independent and you can do some optimizations. And this is one of them. You start running log things and parallels. This makes a difference. And the other one, if you're doing logging or error handling, error generation in a control loop, you may want to take out the bulk of the operation, the actual operation of writing to a file or writing to a string control out of the control loop. So I have an internal worker loop which has a dedicated queue, and you create a cluster and pass it to that queue, and worker loop picks it up and does the actual logging outside the control loop. And this didn't have okay, I want to go into this. Global log is interesting. So 2 things remaining. One, I'll show you how it comes all together. And second, we'll talk about the benchmarks. So this is your error classes, the wrapper, the abstract, the error interface, and my implementation. And this is the log design. It inherits from an R class, which is a base class for my stuff. And they seem not connected to each other, but they are. And they actually need to call each other to perform their activities. For example, the log needs to call get information, error information on the error specs. So it calls the wrapper. And error host needs to log internal errors to the global log. So it calls this way. And the next one is you have the application. It calls the wrapper. It implements some other classes, and it can call both global and normal logs. And then you can start extending your post errors, my basic implementation. So you need to do some other stuff. So This turns out not to be that simple. See? Seems to be simple, even everything is not simple. So my experience is that delivering a scalable error handling solution is not a trivial task. You may want to do it yourself. First, try to look around and see if somebody already has something that fits your needs. Benchmarking. I wrote a special benchmarking tool that actually has several benchmark cases. It can start a regular or an optimized asynchronous log. You set a number of iterations, and you hit run, and you get a distribution, which is a histogram of microseconds it took for this log operation